just to go over the calendar real quick, we're going to start 5.2 and 5.4, which is our next unit. There's homework assigned, but I'll check these homework assignments on Monday, okay? Because I want you guys to focus and use the time today and tomorrow to prepare for your test. The test on Friday, calculator portion, it'll be 3 FRQs. Okay. You see the variations of each of them in your packet. There will be a particle motion problem, a Riemann-Sums problem, which is just a table of values, and then a derivative graph where the g of x equals integral of f of x, and we have to go through that whole process. Okay. All right, so if you're able to work through that packet and I put some extra practice in there, you should feel pretty confident going into Friday. It's not going to veer too differently from those types of problems. Okay. I will bring your calculator on Friday. I will have a separate sheet to give you that has the calculator steps if you feel like you need that. Okay, so I will provide that for you. Okay. All right, so because the test is being pushed back, your schedule is going to feel a little condensed here. We are going to have a quiz next Wednesday, just over 5.2, 5.4, and 5.5. It's just a short quiz, just going through and going through the integral process, U substitution, synthetic division that we've learned. Okay, so it won't take the whole class period. We may even be able to spend a few minutes in the beginning going through 1 or 2 problems before you take the quiz. Okay, so that's what's coming up. Any questions? Okay, help session. I'll do a help session tomorrow morning, Thursday morning, and Friday morning. Okay, tomorrow morning 7:30, and then Friday morning 7:15. I'll send out a reminder this afternoon. Okay. All right, let's go to our notes for today. Okay, so natural log integrals. Now let's think about power rule, or at least the rule that we do know how to, that we would attempt this with. What would happen if we attempted to apply power rule for this particular problem? Okay, so if we attempt the power rule, we know that the variable has to be living in the numerator, so we're going to have to bring that x up. It becomes x to what power? Negative, well, just -1, right? But what's going to happen if we attempt to power rule at this stage? We'll get what, x to the over 0. Okay, and this doesn't exist, right? So this is the one scenario where power rule is not going to be able to get you something that that makes sense. So this is an undefined term. Every other scenario, we should be able to get power rule to work, right? It could be x to -1/2, it could be x to 1/2, it could be x to 3/2, it could be x to the 5th power. This is only one scenario that's going to get you to 0, and that's x to -1. Okay. So this is the one situation where power rule is going to fail. But we have an exception to this power rule that can handle this one scenario. Okay. And that is using this natural log rule, 1 over u du is equal to natural log as to value of u plus c. And this is coming from the derivative rule from first semester. The derivative for natural log of u is u prime over u, or 1 over x, if we're doing natural log of 1 over x, of x is 1 over x. And that 1 over x, if I take the antiderivative, it's going to go back to this form, right? So in other words, we're kind of undoing this calculus, the derivative process from first semester. Okay, so today we're just going to be focusing on this new rule, this natural log rule as the exception. Okay. Now, this is a very common rule. You're guaranteed to see this in one form or another on the AP exam. But I think it's also easy to misuse this rule. And what I mean by that is, I think the tendency is when students see the variables in the denominator, the natural tendency is you want to just go to natural log. Okay? But that's not always the case, right? You only do this is if the variable is raised to what power in the denominator? To the first power, right? So what that means is if we see 1 over u squared, this is not natural log rule. You bring it up, you got to do power rule for this, right? If you see integral of 1 over square root of u, okay, same thing, that's not u to the first power, this is also power rule. Only in this one scenario of 1 over u to the first power are you going to use natural log rule. Okay, so let's look at example 1 here. Integral of 2x over x squared plus 1 dx. Okay, so let's go down our options, right? Our options are, can I expand this problem using power rule? Expansion is not going to work. There's too many terms in the denominator. I can't split this up into individual fractions. If I brought this up to the numerator, it's going to be parentheses to the -1, and we're still stuck not being able to make much progress. Okay, the second option is U substitution, right? So our U substitution looks like that could work. What could be our U value for this problem? Okay, that's part of it. X squared is as a start, because you know x squared will turn into 2x. But the problem is, if we just let this be the U value, we're left with U plus 1, and that's not going to match this rule that we want. So if we want to go through U substitution, sometimes we have to let it be a rather significant portion of the problem. We'll let the U value be the entire denominator, okay? The entire x squared plus 1. Okay, let's see what happens here. U equals x squared plus 1. Okay, du dx becomes 2x. Cross multiply. Solve for dx. Okay, you make your substitutions just like how we've done with previous U substitution problems. Okay, what do you see here? Yeah, so the important thing was the x's had to cancel out. It's just a bonus that the coefficient also goes away. So now you're left with integral of 1 over u du, which matches perfectly with the rule that we just talked about, right? This is, we try to do power rule, we'll fail, but we have this one scenario that can handle this 1 over u, which is natural log. Okay, remember u is only a temporary variable, so you want to bring your original value back. Okay, that's the answer, yeah. Okay, questions with 1? Okay, look at number 2. Too many terms in the denominator, we can't bring them up and just expand. Also, there's that natural log getting in the way. So there's a little bit of trial and error here. What could be a u value that will allow things to clean up nicely here? The ln x, yeah. It's a little bit of trial and error because maybe you're thinking, well, what if it's the entire denominator? Or what if it's just x? Or what if it's just the x inside natural log? Okay, we know it can't just be x because if you want to go through U substitution, if you're only replacing a variable for a variable, you're not making much progress. You're not changing the problem enough to make the problem look different, okay? The reason why it's just natural log of x and not the entire denominator is because we do have to save a little bit of extra for the derivative, right? Whatever the derivative of natural log of x is, it needs to be able to cancel out the remaining term, just like how we're saving this 2x for the x squared to match. So let's see what happens there. So we let the u value be natural log of x. Okay, from first semester, natural log of u becomes u prime over u. So natural log of x becomes what? 1 over x. Okay, cross multiply. Try to get that dx by itself. Right, we make our substitutions. All right, what do you see here? X's go away. We're left with 1 over u du. And now this matches with the rule that we want to use, right? Natural log of the value of u. Okay, questions, one or two? Okay, we're going to skip 3 for now because I need to introduce long division synthetic before we can do 3. So we'll skip 3 and we'll come back to 3 a little bit later. Okay, let's go to 4. Everybody good here? Mm-hmm. Yeah, just going through the scenarios here that we don't do natural log rule unless that denominator is showing exactly to the first power. Okay. Okay. Second page here. Okay, so we're getting a lot more rules that we have to be able to apply. Remember, we have 6 initial trig integral rules, right? But these are ones that fall outside of those 6 rules. We don't have a rule for tangent or cotangent or secant or cosecant. We have rules for tangent squared. We have a rule for cotangent squared, but not these. So these are ones involving specifically natural log rules or involving natural log. Okay, what we're going to do is we're going to just spend the time deriving them a little bit, just to kind of show you where it's coming from, and then also maybe find ways to allow these to be a little bit easier to memorize if we can see some patterns. Okay, so we're going to try to solve this problem by representing tangent in terms of other trig functions, right? So tangent can also be represented as what? Sine over cosine. Yeah, so let's do that. Okay, so we haven't changed anything. We just made it a little bit, we just kind of broken down tangent into its separate parts. So sine over cosine is the same thing as tangent. So I can treat this like its own separate problem. We can go through U substitution. And if we go through U substitution, we can target that denominator. And let's see if this will work out to be a problem that we can actually match with the rule. Okay, so we'll let the U value be cosine of x. Okay, you guys remember derivative for cosine is cosine. Okay, cross multiply. Okay, we make our substitutions. Okay, what do you see here? Yeah, signs cancel out, but there's a leftover -1. Okay, so we'll pull the -1 outside. Okay, so we have a rule that we can handle this with, right? 1 over u is natural log. The negative stays though. Replace the u back in terms of x. So that's where this rule is coming from. The integral of tangent of u is equal to negative natural log cosine of u plus c. But we have x's here, so that's why it's showing up as x's. Yeah.
Couldn't you just use that in the beginning without having to go through all that?
Right, exactly. So that's essentially what you're going to do. You're going to just be able to memorize this, but I want to kind of show you this process, show the U substitution process, and also I think this method is helpful in the sense that just a few of these steps allows me to remember the rule a little better, right? But essentially, we're going to have to be able to memorize these rules, okay? But I want to talk about how this process can kind of maybe help remember some distinct properties about these antiderivatives. Okay, let's practice part B, just going through that process. Okay, cotangent can be represented as what? Yeah, cosine over sine. So do that same process, but now you'll let your u value be sine of x. And we'll see a very similar thing show up. Okay, make our substitutions. And here we see the cosines is the one that's being canceled out. We're left with 1 over u du. Natural log absolute value of u plus c. And then replace the u back in terms of the original variable, sine of x. Okay, so I want to talk about the rules and just some things about this process that can show why the signs are the way that they are. Okay, so first up is you have to understand that the tangent integral is not one of the original 6, right? So we're not going to be able to find it just by working from the derivative rules. So once we realize that it's not the original 6, it's one of the natural log ones, then we can look at what that tangent represents, right? That tangent represents sine over cosine. And that's the way I remember it. I think of tangent as sine over cosine. And if I can think of that cosine as the u value, and also cosine produces a negative derivative, that negative sign. So that's where this negative comes from. Okay. Cotangent, on the other hand, is cosine over sine. And if I can think of cotangent as cosine over sine, then that's where I know that the natural log is going to have a sign in it. Sine's derivative is a positive cosine, so that's why there's a positive sign. The reason why I want to bring up the negative and positive is because I feel like that's a common mistake that I see students make. And I think the reason why is because we associate tangent with positives, right? Either derivative or integrals. We don't associate tangent with negatives. But in this case, it is a negative because of the fact that the u value is cosine, and cosine produces a negative sign, and that's where that negative is coming from. So it's easy to get those two signs mixed up because all the other previous variations of tangent that we've seen and never produced a positive or derivative or antiderivative. Same thing with cotangent, right? We associate cotangent with negatives, but in this case, it's going to produce a positive natural log sine of u because the sine's derivative is positive cosine, and that's why there's no negative that shows up. Okay, so just want to kind of share with you, those are the common things that I see. It's easy to get those two negative and positive mixed up because it doesn't follow the previous patterns that we've seen. Okay, we're not going to derive these two rules, but I do want to point out that secant produces a natural log rule that has secant and tangent in it, and we associate secant and tangent together, and so those two show up here as well. Cosecant, we associate cosecant with cosecant and cotangent, and those two trig functions show up as well. Okay. We associate secant with positive, and we get a positive here. We associate cosecant with negative, and we get negative here as well.
So it's kind of how like the opposite, how like for like derivatives, if it starts with B, it's negative. Like here, it starts with C, it's positive.
Yeah, but it only shows itself for this particular problem, right? The integral of cotangent squared is still a negative cosecant squared. So it's really this one little scenario where things are kind of opposite from what you expect. So I go through this process of understanding that the U value is cosine or sine. I know the derivative is negative or positive, and that's what allows me to remember these a little better at least. Okay, example 5. Okay, let's talk about a problem here where you have a rational function. You go down your list of options. First option is expansion. There's too many terms in the denominator. I can't separate this into individual fractions and be able to make much progress. Second option is U substitution. If we let the U value be either the numerator or the denominator, the derivative is not going to match and cancel out the other side. So we're stuck not being able to do much with the options that we have. So what we're going to do is we're going to learn how to do long division. Okay, so long division, the purpose is not to solve the problem, is to produce the problem in a different form so that we have rules that can handle the problem that otherwise we'll be kind of stuck. Okay, there's two methods there, long division and synthetic. I'll go over both methods. So here's long division method. You're going to pull the divisor outside, the x plus 5. And dividend you'll leave inside here, x cubed minus 6x minus 20. Okay, you've done long division before in the past, but we're going to just practice through the steps here. So the first thing you do is you start off with the first terms. Okay, and we ask yourself, x times what gives us x cubed? X squared. So you put x squared as the first term. Okay, what we're going to do is you're going to take that x squared and you're going to distribute it through the x plus 5. Okay, and you'll put it below this line here. So x squared times x gives us x cubed. Distribute the x squared through. What's next? Plus 5x squared. Okay, so once you created that second row, you're going to draw a line, and you're going to change the sign of every term that you just brought down. So this becomes negative, and this becomes negative, right? And now you're going to add. You're going to add like terms. The first pair is always going to cancel out to be 0, or at least it should. Okay, so x cubed minus x cubed is 0. That's good. Now, do you see any other like terms that can combine here? No, no like terms. So there's no like terms. You bring every term down separately, starting with the highest degree. So the negative 5x squared is going to come down first, then the negative 6x, and then the negative 20. Okay, so now we're back to the beginning. We're going to try to pair up information again. We ask ourselves, x times what gives us our new term that we're trying to match up with to negative 5x squared. Negative 5x. So put in negative 5x next up. Okay, so now we no longer care about the x squared. You're just going to distribute the negative 5x through the x plus 5. Okay, so negative 5x times 5 is negative 5x squared. Distribute the negative 5x through the 5, we get multiply negative 25x. Okay, repeat the process here. You're going to draw your line. You're going to change the signs. So negative becomes positive, negative becomes positive. Okay, so now you're going to add. First term will always go away to 0. Okay. Do you see any like terms here? Okay. We get 19x, and then bring down the rest, minus 20. Okay, back to the beginning. X times what gives us 19x? 19, so put a plus 19 here. Okay, don't look at the x squared minus 5x anymore. You're just focused on that 19 and the x plus 5. Distribute the 19 through, we get 19x plus, and then 19 times 5 is 95. Same process, draw your line first. Change your signs. First term should always cancel out to be 0. Okay, what's negative 20 minus 95? Okay, negative 115. We try to keep going. Can x go into negative 115? Okay, not without dealing with negative exponents. Okay, we're not dealing with negative exponents, so we stop and we call this the what? The remainder. Now, there's a specific way that you want to write the remainder. You want to write the remainder as a way of showing that you can't divide any further. So we have to write it out as negative 115 over x plus 5. Okay, so what's the point of all this exercise? The point is that now we have something that is equivalent to the starting divisional term, but it's a lot easier to find integral rules to handle these separate terms rather than this connected rational expression. So we have to understand that we haven't done any calculus yet. All we've done is we've rewritten the problem so that the integral process will feel easier to work with. Okay, so the nice thing about long division is that it splits this up into 4 problems, and we can just basically handle each problem on its own separately. So the first 3 terms is easy, power rule, power rule, power rule. And the last term, it's just a relatively easy U substitution problem. Okay, but let's do the easy ones first. X squared becomes, okay, next up, 5x. Plus okay, now let's step to the side and handle this problem separately. We'll do integral of 115 over x plus 5. Like I said, this is a relatively easy U substitution problem, right? We can't expand this out. There's too many terms in the denominator. But what's our U value here? Yeah, that's true. We can bring that negative 115 along with it. Okay, U value is x plus 5. Okay, du dx equals 1, dx equals du. You can pull the 115 out in front. We're left with 1 over u du, which is just natural log absolute value of u. And then replace the u back in terms of the x. So once you've seen these types of easier U substitution problems enough, you can just jump directly from here to here without having to go through U substitution, right? You know that your U value is not going to produce anything more than the 1. So if you can recognize this as, oh, this is natural log, I can just jump right from here to here. That way you can save a lot of writing, right? But only do that once you feel comfortable, right? Up until that point, feel free to continue to go through that full U substitution process. But eventually, hopefully, we can save a bit of time and just begin to recognize that this is a natural log problem, and I don't have any leading coefficient to keep track of except what's in the numerator. Okay, so one more example here. We're going to do the same problem, but we're going to go through synthetic division, which is easier, faster, but it does have its restriction. The restriction is that you can only do synthetic division if you're dividing by x to the first power. If this problem showed x squared plus 5 or x cubed plus 5, we have no option but to go through long division. Okay, but this one we can go through synthetic division. Same problem as above. We're going to see the process is going to be a lot faster. First thing you're going to do is you're going to solve for x plus 5. You're going to set that equal to 0 and solve for x, and you'll get negative 5. Okay, so you're going to put a negative 5 outside kind of a half rectangle box. Now, what we're going to put on the first row are just the leading coefficients. We're not going to put any variables in, okay? But we are going to have to make sure that we have a placeholder for every degree that's involved, or every degree that's skipped over. Okay, what's the coefficient in front of x cubed? 1. Okay, next up is x squared. We don't see an x squared, so we need to have a placeholder and put a what in place of it? 0. Next up is a linear term, negative 6. And then finally the constant, which is negative 20. Okay. Yeah, so you're good with the negative 5. The way you get negative 5 is you set x plus 5 equals 0. You're always changing the sign, put it out here. And now you're going to put the coefficients of each of the terms in the first row. So what's the coefficient in front of x cubed? 1. Right? Do you see an x squared? There's no x squared, so we need to have a placeholder for that. That second row is going to be designated for x squared, so we'll put a 0 there. And then the column next is for the linear term, which is x, and the last is for the constant. Okay. All right. So now this is the process. You're going to take that first number and you're going to bring it down below the line. Okay, next up, multiply. Negative 5 times 1 is, okay, you're going to go down and that first open space that you see on the second column, you're going to put that number there. And now you're going to add. 0 minus 5 is negative 5. Okay, now involve the outside factor here. Negative 5 times negative 5 is 5. Okay, 25 minus 6. Multiply 19 times negative 5, 95. Add negative 1. Okay, so now we're starting with x cubed. You're dividing by x. So when you divide by x, all of your degrees we're going to fall by 1. So if I start with x cubed, I'm just going to end up with what? X squared. And once you have that first degree, then you just go down and make every degree 1 less than what you started with. So x squared minus 5, x, 19. So you got degree 2, degree 1, constant, and the last is your remainder. Yeah.
What are you multiplying negative 5 by? Get 25 and negative.
So once I bring the number down below the line, I'm multiplying that number with the outside factor.
Oh, okay.
So I brought the 1 down. Negative 5 times 1 is negative 5. Add. I'm only multiplying with this once I see a number show up below the line.
Where did you get that 25?
Oh, negative 5 times negative 5
Oh, okay.
is 25. And then this combines to be 19. And 19 times negative 5 is negative 95. Okay. So this brings us to the same starting point as long division, but a little faster. And if I go through the same process as before, power rule and then U substitution, I'll get the same answer as before, right? Same problem, different method. Synthetic division is faster, but it only works if you're dividing by x to the first power. Questions? Okay, let's spend the remaining time doing test review. So let's go back to your packet. Go to page 3. Okay, so we have a derivative graph here. So we start off. Go ahead. We understand that G and F have the staggered relationship here. We know F is really sitting at the G prime level because it takes the integral in order to bring that F up to the same level as G. So we can go ahead and build all the way down to G double prime. So we know that G prime must be equal to F of X. You can also go through second theorem to arrive at that, but we can just jump directly to this point. Okay, good so far? So let's just also build something in terms of connecting G double prime with function F. If G prime turns into G double prime, then we can make F turn into what? F prime. Okay, so they're just going to be one off of each other. So anything with G, we're going to rely on the first definition. Anything involving G prime, we'll rely on the second definition. And then anything involving G double prime, we'll use the third definition. Okay, we need this so that we can connect our G with what we want to do with the graph. So you're either pulling the area, pulling the order pair, or pulling the slope. Okay, let's start with G of 2. G of 2, we look at G of 2 as defined as the integral from -2 to x. Replace the x with your x value that you have here. So -2 to 2. We have a semicircle that sits below the x-axis. We know it's going to be area related, but we know it's going to be negative as well. So 1/2 pi r squared is the area for a semicircle. What's the radius of the semicircle? 2. So put 2 in for r. 1/2 pi 2 squared. We get 4 over 2, which is 2 pi. Make it negative though, so we know this must be equal to -2 pi. Okay, same thing, G of -4, go to your definition and replace your x with -4. Okay, I'm trying to read the graph here, so what will we prefer if we're trying to read the graph? Yeah, it's just easier to read from left to right so that we're not to think opposites in terms of positive and negatives. So I'm going to flip the bounds, but I'm going to make an adjustment, pull a negative out in front. Okay, so -4 to -2 is just this little triangle here. 1/2 base times height, so 1/2 1 times 2, I get -1 because it's below the x-axis. But then there's a negative sitting outside my antiderivative, so this will give me what? Just a +1. Any questions so far? Okay, G of 6, again, rely on your definition. Okay. -2 to 6, we have to involve the semicircle and the triangle on the right. This triangle, 1/2 base times height, width of 4, height of 2, area of 4. So -2 pi plus 4. There's no need to adjust the bounds. It's already going from a smaller to a larger y value, larger x value. Okay, part D. G prime of 4. There's the connection here, right? G prime of 4 is the same thing as f of 4. F of 4, we can just pull from our graph order pair. What's f of 4? 2. G prime of -2. G prime of -2 is same thing as f of -2. order pair, so f of -2 is just 0. Okay. G double prime of -5 is the same thing as f prime of 5. F prime of 5, we're not going to pull the order pair, but instead we're going to pull the what? The slope of that line. Okay, so pick a point, 2 points on the graph, and just do rise over run. Down 2 over 2, that's a slope of -1. Okay, part G, for what values of x is G increasing? Remember that this is not the G graph, okay? This is the G prime graph. So go ahead and label what you're looking at. Anything above is positive slope, anything below is negative slope, anything on the x-axis is slope 0. Okay, let's create our G prime sign line so we can just look at the arrows and decide, and just also use it for future reference. We're going from -4 to 6. Okay, where are the critical points? Good, and 2. That's it, right? Just -2 and 2. Okay, don't look at the rise and fall of the graph. Look at where it's located. Is it above or below the x-axis? Everything up to -2 is below, so that's going to translate to a negative slope. Between -2 and 2, still below, and between 2 and 6, above. So now we can tell that our graph is increasing simply between 2 and 6, right?
I know it's a G prime.
We know it's a G prime graph because of this relationship here. G is the antiderivative of f, and then they're telling us that this is the f graph. So if this is the f graph, we know f is a G prime because of this relationship here. Yeah. Okay, so our G graph is increasing. From 2 to 6 because G prime is greater than 0. Okay, for H, we just rely on the table again, or our sign line again. Make sure you put a union or comma between each subinterval here. Okay, find all points of inflection. How do we find points of inflection off of the derivative graph? Yeah, slope changes, right? Peaks and valleys. Okay. So -2, 0, and 4. I'll create a concavity sign line here. Now we can look at the slope, right? Anything that resembles positive slope is going to translate to concave up. Negative slope, concave down. Positive slope, concave up. Negative slope, concave down. There's a change in signs for each of these critical points, so we know there's 3 points of inflection. Because G double prime changed signs. Okay, find the absolute extrema. So find absolute extrema. This is EVT. So to do extreme value theorem, what candidates did we look at? Yeah, relative min, relative max, and endpoints. So just look at your slope sign line. All you need is to look at this, right? Don't include -2. -2 is not a relative max, relative min. You're just going to test G of -4. You'll test G of 2, and you'll test G of 6. Okay. Do we have some of these values already? G of -4 is 1. G of 2 and G of 6. Yeah. Now, if it didn't show up before, then you would just go through and find the area, or go through the definition separately. Okay, so negative 2 pi plus 4, that's around -2. This is -6. Okay, so this is the smallest value, that's the largest value, right? So we can say absolute max is 1, and absolute min is -2 pi. All right, questions? Okay, study for your test. Your test is Friday, help session tomorrow morning and Friday morning. Have a great day, guys. $7:15.
Is it okay if those questions would involve pi that you include like a simplified form of it? Because I got -6.
Yeah, leave it as that value.
Okay.
Bye, have a good day. Bye, have a good day, thank you.
Do we not need because statements for the extreme values?
No, just show your candidates and then make your.
Okay. Thank you.
I'm saying, so I have a high school state on Friday afternoon, and I'm not sure if I'm going to be yet. I'll know more later today. So, it's like usually, so I might be here, but I might not be, just so you know. I'll let you know tomorrow when I kind of figure that out.
Okay.
So.
If not, then just find a time on Monday.
Yeah, that works for sure. All right, thank you.
All right, see you.
Oh, okay, yeah, all right. And it was white guy reading it, he was like, I'm not gonna read that.
That's nice. It's my parents were both born. I mean, the other ones look at. Just like hardly. I know.
On the outside. So X. They're kind of in line, and then you had
So you
another.
saw Braxton used to live.
Dude, if you ever have enough racks, the locker room would have sucked.